All right, the next concept on weak acid-base equilibrium is looking at weak bases. Now, a weak base, symbolized as B, again, will provide water has to be a part of the reaction because in order to be a base has to accept a proton. Well, you have to have a proton donor. So in this case, water is acting as the proton donor. So you must have water being part of a weak base problem. This is partly why I always say add water for a weak acid too, so you're not confused as to when do I add water and when do I not add the water. Now the base then becomes a conjugate acid, which means it has added the proton to it, H+, and the water now has become hydroxide. Now sometimes the misconception is that the substance produces an acid, so it's acidic, but the key thing is here. The hydroxide ion is a strong base, and the Hb+ is a weak acid. So the strong base significantly affects the pH much more than the weak conjugate acid does. So with that, that's the reaction of a weak base. The weak base will actually, instead of donating a proton, will accept the proton from water, forming hydroxide. So to write the Kb expression, products go on top. So we have the conjugate acid goes on top. The hydroxide goes on top, all over the formula of the weak base. This is the Kb expression. It is on the green sheet, just like the Ka equation from the previous lecture is on the green sheet. So both Ka and Kb are given to you. You just have to understand what the Hb+ and B represent, and just a matter of putting in the different substances. Okay? So here's an example, again, of a reaction of the fluoride ion in which it reacts with water forming hydroxide. So the Kb expression here would be the concentration of HF, concentration of hydroxide, all over the concentration of F-. Again, water is not included because water is a liquid and therefore is not part of the Kb expression. All right, I'm going to pause the lecture real quickly for A, B, and C here. Write the reaction of how it responds to water, and then write the Kb or equilibrium expression for each of these. All right, so there you can see in each of these cases, the substance acts as a weak base, so it pulls a proton off of water, forming hydroxide ions, and the Kb are the two products over the weak base. Again, the only thing that's not included is water because it's the only thing that is a liquid. All right, moving to the bottom of this page. One key concept, as we saw also for acids, is that the stronger the base, the greater the Kb value. So the higher the Kb, the stronger the base because more of it dissociates, and it also produces a higher amount of hydroxide ions. Okay? And vice versa, if you take the negative log of Kb, this is called the pKb. And as before, the greater the pKb, the smaller the pKb is. So again, the relationship between the pK value and the K value. So the larger the value of Kb, the stronger the base. One other thing is when you have an acid-base pair, and again, as review, an acid-base pair like above in letter A, the base is the nitrite ion, and the acid is the nitrous acid. When you have an acid-base pair, something that's separated by a single proton, the base has a Kb value, and the acid has a Ka value. In every acid-base pair, the Ka of the acid times the Kb of the base will always equal Kw, which we know has a numerical value of 1 times 10 to the negative 14th. It's on your green sheet. So down here you can see a lot of different acid-base pair systems. And for example, if you take, for example, HF and F- and you multiply those numbers together, I can guarantee you that they'll multiply to a number that's very close to 1 times 10 to the negative 14th. Okay, so if you know the weak base, the conjugate acid of the weak base is simply 1 to the negative 14th divided by that. So if you know one, you can always find the other. All right, let's turn the page. Okay, so let's look at example letter A. calculate the concentration of hydroxide ions in a 0.15 molar NH3 solution. So NH3 is the 1 weak base that I told you should have memorized. But right away, when you see a Kb value, just like for acids, if the Kb value is less than 1, this tells you right away that it's a weak base. And therefore, it's a weak base. The weak base will pull a proton off of water. Oops. Forming the conjugate acid and the hydroxide ion. So, again, we write the words ice. The water column crosses off because it is a liquid. The initial concentration is given. The other substance we assume to be 0 because no other information is given. And before any of the ammonia can pull off a proton, the initial concentrations are 0. Minus x, plus x, plus x. 0.15 minus x, x and x. So now we substitute into the Kb equation, which we do know the value of Kb. Now to solve for x, we never use the quadratic formula. And again, because Kb is on the order of -5, it is small enough that we can use the 5% rule. So therefore, this x gets eliminated. And we have 1.8 times 10 to the -5 equals x squared over 0.15. So now we're going to solve for x. So you pull your calculator out. And we get a value of x being 0.00164. Now, the value of x, what's critical about it is it tells me the concentration of hydroxide ions. And if I know the concentration of the hydroxide ion, I can now find the pOH by taking the negative log of this. And we get 2.78. Now, this is the part of bases that's a little bit different. So in the acids, we found the value of x, we take the negative log of it, and we get 2.78. Too often students stop here, but when we do a base problem, it involves one extra step. You have to understand when we take the negative log of the x value, that's the pOH, not the pH. So if you were asked to calculate the pH of this solution, you would then have to take 14 minus this number, and that would give us a pH of 11.22. Now, I know they didn't ask us to do that, but I wanted to show you how you'd calculate the pH of a weak base. You find the pOH first, and then you subtract from 14 to get the pH of the solution. The question did ask what the concentration of hydroxide ion was, which this would have been our answer right off the bat, is the value of x, because that tells me the concentration of OH minus in molarity. All right? Okay, now what I'd like you to do is pause the lecture now, and when you restart the lecture, you will see both the solutions for B, C, and D provided. I'd like you to give them a try first before you do start the lecture, and then we'll see how well you did. All right, so good luck. All right, problem B was pretty much the same exact example as the one I showed you in A. Again, we had to do the ice table with a 0.1 molar initial concentration, use the 5% rule as you can see, and then we get an x value of 1.18 to the -6, and taking the negative log of that, we get a pOH of 5.93, and then we got to subtract 14 minus 5.93 to get a pH of 8.07. Again, if it's a weak base, more than likely the pH is going to be basic, and we should see a value that is over 7, which we do. In letter C, they give you the Ka, which you have to know. The Ka would be the acid of the conjugate base. And if the acetate ion is the conjugate base with an unknown Kb value, the Ka must be its conjugate acid, which in this case is acetic acid. So the Ka for acetic acid is 1.8 to the -5. So what is the acetate ion Kb value? Again, we just use the Kw equation, and dividing, we get 5.56 times 10 to the -10th. Letter D is a little bit harder of a problem. we're using the same technique, but in this one, we don't know the concentration of the weak base, the hypochlorite ion. So I just put in an arbitrary value of A. I didn't use X because we use X for the change. So we get A minus X, X, and X. So I get the Kb equals X squared over A minus X. This is a little different of a problem in the fact that we're used to seeing the initial concentration given, but this problem, that's actually what they're asking us to find. We are given one more piece of information, which is the pH. So immediately 14 minus that gives me the pOH. And then working backwards, 10 to the negative pOH gives me 3.16 to the negative fourth is the value of X. So I can now substitute this into my table. While it's pretty ugly, I have everything given up there except the value of A. So then I move this A minus 3.16 term over. I distribute, solve for A. And when you get done with A, you get a concentration of 0.303 molar. They didn't ask for the molarity, they asked for the moles, and they said it was 2 liters of solution. And again, molarity equals moles over liters. So if I know the volume and I know the molarity, multiplying those two will give me the moles, and I get the final answer of 0.606 moles. They could take it a step further and ask for the number of grams, if it's a solid, which sodium hypochlorite is, and then you could simply convert the mole quantity into a gram quantity by using the molar mass of sodium hypochlorite. So that's about as difficult of problems you could have, and one that I did want to share with you in doing problems with Kb. But for the most part, it's still the same technique. Do the ice table, plug into the Kb or Ka expression, depending on if it's acid or base, and then solve for the missing variable. And that's pretty much it over and over again. Okay, let's turn the page. All right, the last concept here is something called hydrolysis. And hydrolysis is looking at how a salt can potentially affect the pH of water. Some salts do and some salts don't, and it depends on what the cation and anion are. Now again, definition, a salt is any ionic compound where the cation is not H plus and the anion is not OH minus or peroxide. So, great example right off the bat is sodium chloride. Sodium is not H plus and chloride is not OH minus or peroxide. So whenever we have an ionic compound that doesn't meet that criteria, then it's a salt. Now those salts, if they're soluble in water, will dissociate, and even if they're very insoluble, a small amount it will be soluble. So we always treat it as being somewhat soluble. Well, sodium chloride, potassium carbonate, and aluminum nitrate are all readily soluble in water, and therefore they dissociate. So real quickly, pause the lecture now and write the dissociation of all of these 3 salts as to what they do when they are placed in water. All right, sodium chloride dissociates into a positive sodium ion and a negative chloride. Potassium carbonate produces 2 potassium ions and a carbonate ion. And aluminum nitrate produces aluminum ion and 3 nitrate ions. Again, when you are done, they better be balanced not only in atoms but also charge. Make sure the charges are balanced. Okay? In this case, they all summate to 0 if you properly do it. Okay? Now, the question becomes, could these potential ions affect the pH of water? And the ions that can affect water are such. Ammonium ions are conjugate acids, is a conjugate acid from ammonia. And therefore, any salt containing ammonium has got potential acidic properties. Other acidic compounds come from the cations. Excuse me, I didn't read first. The cations that come primarily from group 1 and group 2, except magnesium. We talked about magnesium hydroxide being an exception last time. So primarily, most of the metals in group 1s and 2 are spectator ions. And whenever something is a spectator ion, what that does is it does not affect the pH of water. Therefore, if you put it into water, the pH stays around 7. Okay? Cations that do affect or are acidic tend to be metals in the D block. Many of the D block metals tend to have acidic properties, okay, including also aluminum, which is in the P block. However, while this is true, they have taken this type of chemistry out of the national exam. So really the only one I tell students to worry about is ammonium. Don't worry about these other D block metals that can be acidic. Now, application of this, do understand that if you have iron or copper in your water, which is very common in this area, if you have iron or copper in your water, these tend to make the water that you are drinking acidic. I'm not going to go through the chemistry of it, but understand that these ions, they're metals in the D block, and therefore they do have, if they're leaching into water, can cause the water to be acidic. And it does become an issue if you have like copper pipes or other metal pipes that carry water. And the fact that over time that could bore a hole through it, and then you could have leaking, which is a common problem with a lot of copper pipes after 10, 20, 30 years of being used. All right. The weak bases are primarily any anion of a weak acid. There are 7 strong acids. All of their anions are spectator ions, and there's one missing from this group, so please add the chloride ion. All 7 of these ions are spectator ions, therefore they do not affect the pH of water. So group 1 and group 2 metals and the anions from the strong acids, these are the spectator. These are the spectator ions. And again, make sure you include chlorate here. Any salt containing these ions, any combination of these ions, would be a salt that does not cause the pH of water to change. However, any other anion that comes from a weak acid, for example, HF is a weak acid. The anion of it is F-. F- is a conjugate base and therefore will make water basic if it's a salt. So if you have, for example, something like sodium fluoride, sodium is a spectator ion. It does nothing to water, but the F- will. So if I dissolve sodium fluoride into water, that fluoride ion will make water acidic. How? The fluoride ion is a conjugate base. And what do conjugate bases do? Conjugate bases accept protons. So it'll accept a proton from water, forming HF, and what's left behind is OH-. And right here. So when you add sodium fluoride to water, the fluoride ion hydrolyzes water. The fluoride ion hydrolyzes water, forming hydroxide ions. And that causes the pH to be greater than 7. So by that salt has the ability to hydrolyze water and causing the production of hydroxide ion to be greater than what it was before the addition, and that makes the water basic. Acidic, primarily, as I said, it's a lot of this metal chemistry which they've removed from the national exam. So the only one you really got to be worried about is ammonia. When you add ammonium or any salt with ammonium, for example, ammonium chloride, you'll notice that chloride is a spectator ion. It's not going to do anything to water, but the ammonium is a conjugate acid from the weak base ammonia. So ammonium ions, when they are present in water, will donate a proton to water, forming H3O+ and NH3. Now we see that the production of H3O+ is present. So any salt containing ammonium ions, the ammonium ions hydrolyze water, donating a proton, forming hydronium ions, and that causes the pH to be less than 7. So any salt containing ammonium will make water acidic. Any salt containing an anion from a weak acid has got basic properties and will make water basic. What happens if we have a salt combination of ammonium fluoride, where both the NH4 is a conjugate acid and F is a conjugate base? Here it depends on the value of the Ka and the Kb. If NH4 has got a greater Ka value than the F- is Kb, then it's acidic. Vice versa, if fluoride has got a greater Kb value than NH4 is a Ka value, then it's basic, which I don't really expect in the national exam. all I want you to take away from this last part of this lecture is to understand that when you dissolve a salt in water, they do have the ability to change the pH of it depending upon if the salt contains ammonium or the anion is an anion from a weak acid. So it's critical that you know your 7 strong acids. Because if you know the 7 strong acids, you know the anions that are spectators. Any other anion in a ionic compound will cause water to be basic. Okay? Not a concept I would put a ton of time into. As long as you understand that weak acid, weak base stuff, that'll be the primary focus of this unit. But just be aware of this ability of salts being able to hydrolyze water. All right? Again, thanks for listening.